All right, 16.5, we have surface integrals of vector fields. Surface. All right, now things actually start getting a little fun here. So we given some surface. Again, this is just going to be a brief explanation. If you want to look this up and get a better understanding of what is going on here and the math that kind of proves what I'm about to say. So let's say we have our surface. This is our surface. There it is. Okay, and then now we have some sort of vector field that's applied to this space. So let's just say coming through here, there's some vectors. So this represents, and these they don't even have to point in all the same direction, right? So there's some sort of field going on here. Okay, so F. This represents, all these arrows represent F. Okay, that's our vector field. Everything in red there, you see. Okay, now let's take a look at just one small little area. So I'm going to redraw just that little piece of this. So let's say at one part here, let's say the vector of the field that's associated just at that single point is represented by this, say. So let's say at this point, this is F, one particular vector. And again, everywhere the vector field can be different at every point on here, or it could be the same as well. Okay, so let's just say that. And then let's look at our normal vector. So the normal vector would shoot out here. So this is it. Now, to make this brief, we want to know at this point, we want to know how much of this force or this vector field, how much of this, and it can be a force field too, how much of this vector is contributing to in this direction. At this point, we just want to know, again, how much of this is contributing in this direction. And to make a long story short, if you remember about the dot product between these two angles is involved in calculating the projection. So think about if you look at this vector pointing here, and if you're talking about the projection onto N, which is just this little piece here, we're interested in this little piece. How much of this vector is contributing in the normal direction at that point? And again, if you remember about this theta, that dot product is involved in that. All right, now, before we actually get to some sort of formula, we should talk about what flux is. So flux is involved. It can relate to fluid flow. It can relate to magnetism and different things in electromagnetic fields. It can relate to gravity, anything that's going on. But flux then is defined as a rate. Okay, the rate of flow through a surface. Like, for example, if you're looking at a cross-section of a pipe, maybe you're looking at some sort of pipe. There it is, and maybe it's like it's reduced, and you have some sort of flow coming through here, and something is going on here. We might need to know, if like we look at this little cross-section here, we might need to know the flow through here, and then after it's reduced, we might want to talk about the flow through here, and any increase or decrease that's happening because of it being a narrower diameter or a bigger one. So we're just looking for the rate. Okay, now, so a vector surface integral is going to look like this then. All right, notice it looks very similar to what we just had, but before we had f ds, where ds is actually that magnitude of the normal, and then du ds, or sorry, du dv. That's what ds represented in, and then f was our f of our parametrized function. But this one is actually, because it's a vector surface integral, and we want to know about this angle here, so we can get this projection basically in the n direction. This is now a dot product. Okay, so all we're going to do now is take the double integral over d, and we're going to dot it to the normal vector. Okay, and that will basically adds up all those vectors. So what this is doing, it's adding up all these vectors across this surface, but only in the direction of n at each point. And of course, if you have some sort of, whatever, maybe it's like a little part of a hemisphere or something, right? At each point here, the normal is going to be this way, normal is going to be this way, normal is this way, normal is out here. So see, the normal can be in any direction. It's not necessarily in one, because this might look like a plane to you. So it's going to take all the sum of these vectors, but only in the direction of each n at every single point there. All right, let's clear that up and let's get an example up here. All right, so we're going to calculate the flux of the vector field through this given surface Now, one thing that I don't think I covered maybe at all or even thoroughly is we have to talk about what direction. Certainly, if you just looked at that pipe cross section, it would certainly matter if the velocity flow of the water was heading to the right or heading to the left. The flow that we're looking at, we have to basically say which side is positive. And I think I talked about that in the one figure a little bit, but without spending a whole lot of time on it again. We want to make sure that we talk about which side of the surface is in the positive direction. So we're going to say it's oriented with the normal pointing in the negative y direction. Now I'll show you why we're choosing that one. All right, so I had that y is equal to 1 plus x squared plus z squared. Now, just normally when I'm using this GeoGebra, just to make sure I know which one is the X, Y, and Z, I usually just plot a point, like 1, 0, 0. And I plot that, and I look right here, so that tells me that the red one is the x-axis. So we orient it like this, because the x and y is not labeled as x and y, I don't think, ever. So this is why all right, so if we look at this, let me actually just capture. And then let's come back over here. Where are we at here? Here. All right, so let's look at why we're choosing this. So we're basically saying that the outside is in the positive direction. So if you look at it, it says oriented with normal in the negative y direction. Now, that's not true for everywhere. So it doesn't matter where these are. Notice that even if you come off the top here like this, that's what the normal would be here. That's what the normal would be here. That's what the normal would be here. Do you see that they all kind of go in the negative y direction? That they all on the outside go that way. If you were to choose or orient the surface with any of the vectors on the inside, say in here, that they would be, even one here, that they're all heading basically in the positive y direction. So this is negative y, positive x, positive y. So we're basically orienting this with all the normals pointing to the outside, okay, which is, right? So what we're trying to do is we're trying to find this vector field, this force field, whatever it happens to be. We want to know how much of this is basically shooting out of that surface. It's passing through the surface this way, passing through the surface, passing through the surface, passing through, even here, passing through the surface, going out. We're saying that from the inside, heading out is the positive direction, and from the outside, heading in is the negative direction. Okay. Okay. Now, step 1, find a parametrization. All right, so we want to find, now remember I said a real easy one to do was like u of uv, was like uv some f of uv. But this f, you could certainly have f of uv, uv. It doesn't matter where this f is. It can be in any position as long as two of them is just u and v. And they can really be anything as well. All right, to make this, let's just go through here. If you look at this, y is defined, and this, so what we have already, here's what we have already. We have y defined as a function of the others. Do you see that? Right, so think about if you let, g or whatever, just make some function up, or even f. There's f. So we have some function of x and z is just 1 plus x squared plus z squared. So we already have y defined as a function of the others. So in order to make our function, that means that our y value is going to be 1 plus x squared plus z squared. Okay, And then we can actually make this, since I'm using x and z here, we can make this x and z instead of u and v. Oh, there we go again. Oh, I hate when that happens. All right, this is x. This is y. I ain't messing around with that. And then this can just be x, and this can just be z, right? All right. Oh, I did not give you, and I always keep forgetting this, I did not give you the restrictions here, up here, because I'm looking at where I got these numbers from, and I can't figure it out. That's because we're looking at through this surface only for y between 1 and 5. Okay, so if you look at this, so this is actually, if you look at where y is 1, x and z would both have to be 0, right? So we're looking at from here to 1, 2, 3, 4, 5. So we're looking at this piece right here. All right, so just all this stuff. All right. And then we have to look at our domain then. What is the domain of this? Now our domain is actually going to be on the xz plane. So there's going to be this circle right here, which is formed here. So that's going to be our D because we're oriented this way. Okay, this is actually a good problem because z is not a function of x and y, because we do a lot of those. At least this one now, y is a function of x and z. So there's our domain there. So since, let's see, since y went from 1 to 5, y is between 1 and 5, and y is 1 plus x squared plus z squared. That means y, which is 1 plus x squared plus z squared, is equal to 5, and then subtracting 1 from each side. That means our domain goes from, okay, so x squared plus z squared is between 0 and 4. Okay, next we're going to compute the tangents. So we're going to have in the x direction, we're going to have the z direction, and then we'll calculate the normal from there. Okay, so in the x direction, derivative of this with respect to x is 1, derivative of this with respect to x is 2x, derivative of this with respect to x is 0. Derivative of this with respect to z is 0. Derivative of this with respect to z is 2z. Derivative of this with respect to z is 1. Okay, our normal then is the cross product. Now, when we do this, you can do this cross product in either order. But if you do it in either order, if you remember your right-hand rule, that if you do, like say, I cross j, could say get k. If you do j cross I, you're going to get negative k. So we have to make sure when you do these that you're oriented in the same direction as the previously stated orientation. Okay, and I'll show you what that means in a second. So covering up I, we get 2x minus 0, so that gives us 2x. Okay, remember this, we have to worry about a negative for the j. So covering up j, you get 1 times 1 minus 0. So that 1 times 1 gives us 1, but since the j1 is negative, that's negative 1. Covering up the k column and row, you get 2z minus 0, so that's 2z. Okay, so there's our normal. All right, next, we have to take our function, and we have to find f of our parametrization. All right, I have a random thing here. All right, let's see, we're at step 3. All right, so we have to find f dot n, but we don't even have this f yet. To find f, we have to find f of our phi. All right, so recall, let's write down what is our f. So f of this to negative yx. All right, so actually plugging in our phi then, our function, which is x 1 plus x squared z. Okay, I think I can show this. All right, so this is our, basically our, this is where it gets confusion if you don't use u and v, because we have x's here, x's here. They're not all the same x's. All right, so this is x, y, z. So into f. So f says the first one is 2. So that's just 2. That's not a big deal. And then plugging this into here, which is, it says negative y. So this represents y. So the negative of that is negative of 1 plus x squared plus y squared, or z squared. And then plugging in the x value, we go to look for phi, and that is just x. Okay, now we can do f dot n. So we're going to do f dot n. So it's 2, and then negative 1 plus x squared plus z squared, x, dotted with the normal, which is 2x, negative 1, 2z. All right, so that's 2 times this, which is 4x squared. No, 4x. And then this times that. So negative 1 times that just negates all that, negates that negative. So we're just left with 1 plus x squared plus z squared plus x times 2z is 2xz. All right, I'm going to need a new page. All right, so right now, step 4 then is to write out our integral. Or just 4, I don't think I put the word step. So our integral, surface integral, at f dot ds is the integral on d and I'm just going to write it out, x squared plus z squared plus 2xz plus 4x plus 1 dx dz. And then our domain, of course, is this circle with radius 2, r equals 2 here. All right, now, so for here, okay, so this is x, this is z. Okay, this is the positive x direction, this is the positive z direction. So this is our d. Y direction is coming straight at you. So there's no y in this picture. Now this is on the xz plane, of course. We have a radius of 2. So because this domain is circular, we're going to need to do a change of variables on this. Now, notice now that we're not really involved with that surface anymore. We have an f dot ds right here. So this involved the surface. We need to integrate over this domain. Because this is circular, or a disk, we're going to do a change of variables now. It's just going to make it easier. Now this change of variables, of course, we're going to change of variables. We're going to make it polar. Because we're integrating this function over this domain, but because this domain is a circle and it's a two-dimensional domain, we're going to make it polar. All right, so now if we have x squared plus z squared is equal to r squared, that means x is equal to r cosine theta, and we're going to let z equal r sine theta, and then of course r is, we know r is, well, from 0 to 2, but let's not write that down. Okay, r squared is x squared plus z squared. All right, so in order to do that, if you recall, so this again is another recall from a few units ago, probably even last chapter, that when we do a double integral of some function in dx dy, just remember when you do your, so we have f of cosine theta, sine theta. Okay, remember we have to add this r, remember that? And then dr d theta. So that's just as a recall, we need this r right here. Okay, so let's write this out. All right, so we're going to replace all of this in using our change of variables. So notice right here, we have x squared plus z squared. Well, we know that x squared plus z squared is r squared. So this just turns into r squared. So r squared plus, well, we have 2xz. So, and here's x, here's z. So we have 2x times z is r squared cosine theta sine theta plus 4x. So we have plus 4 r cosine theta plus 1. Now all of that is multiplied by r, and then dr d theta. And then r ranges from 0 to 2, and theta goes from 0 to 2 pi. okay, because we're integrating this whole circle, 0 to 2, and 0 to 2 pi. All right. Now, let's do the inner. Now, because of the inner, I'm going to change the order of the order here. I'm actually going to do theta equals 0, 2 pi, and then r is equal to 0 to 2. So I'm changing this. So blah, 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 d theta dr. So I'm going to change that. Now, one reason I changed that, and I think the book does a similar problem to this one, I think they leave that. I'm changing it because this r, that's right there, because I'm doing d theta first, so I'm going to do from 0 to 2 pi d theta, that r is a constant. So I'm going to bring that r basically outside of this and put it here, but I'm not really going to consider it because when I'm done, I'm going to leave that r, which is here, which is a variable when I do it dr. So I'm just going to yank that sucker right out of there and forget about it. Okay, and then I'm going to integrate everything else here. So r squared, 2r squared, cosine, sine, and then d theta. All right, so we have the r. All right, so integrating this with respect to theta gives us r squared theta. So, oh, this r is here, so let me put this here. So I have r squared theta plus all right, I'm going to leave the 2r squared there because that has nothing to do with anything. Now, off to the side then, if you think about the integral of cosine sine, okay, d theta, if you let u equal sine theta, and then du is cosine theta d theta, and then d theta is du over cosine theta, and then we have cosine theta sine theta, which is u, and then d theta is du over cosine. Okay, so those cancel, leaving us just integral of u du, and then the integral of that is u squared over 2. Okay? So you got all that? So when we do that then, the integral of this, since u was our sine squared, sine squared over 2, and then that 2 is going to cancel that 2, so we don't even need that anymore. Let's just get rid of that. And then we're just left with r squared sine squared theta. All right, so all I did was integrate 2r squared cosine theta sine theta. There's the work over there. If you want to follow what I did, that's the answer I just got. Okay, plus, I just did a u substitution. Now I have 4r cosine theta, so the integral of that is just 4r sine theta. And that one stays positive, yes. And then this one is just theta. And then all of that is going from 0 to 2 pi. Okay, and this r is going to hang out in front there. All right, so plugging in 2 pi into, and this is theta is equal to 0 to 2 pi. So we have 2 pi r squared plus, so 2 pi here. So sine of 2 pi is 0. 0 squared is 0. So all of this becomes 0. Plus sine of 2 pi, so all of this also zeroes out. Plus theta, which is 2 pi. Minus, now we're plugging in 0. Okay, so 0 for theta here, 0 times r squared. This gives us a 0. And then because sine theta is still 0, then this zeroes out. And then this zeroes out because sine of theta is 0 here. And then because theta is literally 0, that is 0 there. So what we're left with here is r times the quantity, 2 pi r squared, plus 2 pi. Okay. Now that we're going to be integrating with respect to r, we can put all that original r that was out in front back in. So we have 2 pi r cubed plus 2 pi r. All right, that was the inner integral. Now we have to do the outer integral. And then that's from 0 to 2, right? 0 to 2. And we have 2 pi r cubed plus 2 pi r dr. I'm going to put that over here. So we have 2 pi r to the 4th over 4. Right? Let's pull this 2 pi out in front. I don't like that 2 pi out there. All right, so the integral of this is r to the 4th over 4 plus r is r squared over 2, and that's from 0 to 2. All right, so we have 2 pi. So 2 to the 4th, 2, 4, 8, 16 over 4 is 4. Plus 2 squared is 4 over 2, which is 2, minus, and 0 here goes to 0 minus 0. So we have inside there, we have a 6. So we have 2 pi times 6, which is 12 pi. Well, on this last problem, I forgot to talk about one thing, and this is important. And I just went because I just assumed that I knew what I was talking about. And I did, but I forgot to mention it to you guys. All right, there's our surface. All right, this is +1, so it's up a little bit, but who cares? Remember we said that the normal, we oriented the surface in the outward direction, basically. So in a negative y direction, right? Negative y, we said, was the positive direction. This is the positive direction. Well, let's look at our, let's see, the normal we actually found. And remember I said that when we did the, let's see, I forget if I did it, which way I did it. Let's verify. I did the tangent in the x direction crossed with tangent in the z direction, actually. All right, when we got that result, we found that the normal vector was 2x minus 1, 2z. Now, these two here, unimportant. Notice, though, this is the y direction, that when you get this normal, it will either point always to one side or the other side the entire time. Notice, though, that the y, now again, these, we don't care about this. The y direction is -1. So in the normal, we have who cares, -1, who cares. So using these, of course, the x and the y, or the x and the z, contribute to the components of the total vector, but notice that the y direction is always negative. Even if that were like, negative y or something there, that it's always going to have to be pointing in the negative direction. So that means our orientation is okay, that this is acceptable. This is okay to use. Now, if we did t cross tz cross tx, whatever we were going to get here, right, also doesn't matter, but we're going to get this vector in the opposite direction. So it would be negative 2x, 1, negative 2z. So this right here would be bad. Okay, we wouldn't be able to use this. So you would just take this and multiply everything by negative 1 and get the normal direction in the opposite direction. Okay, so you have to use either the normal you find or negative of the normal, whichever one agrees with the orientation that is set up in the beginning of the problem. Okay, I didn't talk about that, and just interject that there somewhere. Okay, I'm just gonna talk briefly about flow rate and do one example, 12 different ways, and then we're done. Okay, so flow rate through a surface then can be found, which is just a calculation of flux, which is a flow rate through a surface, is if you have a velocity vector field and you dot that to ds. All right, so this is the same exact thing that we have. So for an example, this is absolutely nothing new. This is the same thing, but now instead of by just saying that our vector field is a velocity vector field of some sort of fluid or flow rate of anything. Okay, so our example is, now we're going to revisit our old friend, this triangle, with vertices at 1, 0, 0, 0, 1, 0, and all that. All right, so okay. That's just our two-dimensional surface right there. And this is 1, 1, and 1 in the x, y, and z directions. Okay, and then our problem is we have a fluid flow. And that's in meters per second. And we're going to calculate the flow through T. Oops. All right, so we're going to have to find our parametrization. All right, so in order to do that, the surface is a plane. So in order to do that, we're going to need the normal, but we're going to need the normal anyway. So this is really not a bad thing to do here. So if you recall that what this was from previous, this vector, let's call this, it doesn't really matter, let's call this vector A. Call this one B, whatever. So A is equivalent to, if you do the subtraction here, it's going to be 1, let's see, 1, 0, 0, 1, negative 1, 0. And then B is, let's see, that one minus that one, 0, 1, negative 1. Okay, so I'm looking for the normal here, so that normal is going to come shooting out here. And I'm just going to cross those, of course. A cross B. So that's going to be I, J, K. And we did this before, so if you remember what it was, you can. I might put parentheses there. Okay, so I here is going to be zero, 1, negative 1. Oh, this one's negative 1. All right, so I here, it's going to be negative 1 times negative 1, which is 1 minus 0. Covering these up, and this gives us 1 times negative 1, but this one's negative, remember, so that one gives us 1. Covering the k's up, you get 1 minus 0, so 1, 1, 1. Okay, so there's our normal vector, which we're going to be able to use. Okay, so to find this plane, then we can do any point on there. So let's do 1, 0, 0. So I'm going to take the point. So I'm basically going to, again, do P times N is equal to Z. So 1, 0, 0 dotted with 1, 1, 1. Okay, gives us 1. So then that tells us that X, Y, Z dotted with 1, 1, 1 gives us 1. So then we have X plus Y plus Z is equal to 1. Okay, so that's the equation of our plane, but that's the equation of our plane in straight up XYZ coordinates, but we have to find this this mapping function, this parametrization. Okay, in order to do that, you can pick any one of these, since these are all to the first. I'm going to solve for Z. So that tells us that Z is equal to 1 minus X minus Y. Okay, and then our formula then is, you just put XY here, who cares? It's going to give us X, Y, 1 minus X minus Y. So there's our parametrization right here. And the good news is we already know the normal of this. We already know the normal is 1, 1, 1. But we have to make sure it's the right normal. And I know this is going to be a little bit confusing, and it is a little bit confusing at first. Consider this was 2, 2, 2, or 3, 3, 3, or maybe a unit normal in that direction, right? Let's see what this would be. 1 squared, 1 squared. This would be 1 over root 3, 1 over root 3, right? 1 over root 3. I think I'm correct. I just did that quickly. All right, so that would be a unit normal in that direction. But which normal do you use? And the problem comes in is that even though all those vectors are the same, you have to use the normal that's found by doing it correctly here. And that's where the problem comes in. That you can't just pick a random length normal vector. Like usually when we're, I almost said normally. Generally, if we wanted to find a normal vector and plug that in for these, you could use any normal. You could use 2, 2, 2, and when you make these calculations, just if all your numbers are twice as large, you would divide, and you would still get the same equation. But when you use this normal vector, you can't just choose a random normal vector. You have to find the normal vector that you get from this. Okay? And we have to be clear on that. Okay, let me show you what I mean. So we got to find D for this first to help explain what's going on here and which normal is the actual correct normal to use. Okay, so let's look at if this is the function we're going to use. See, if we draw a picture of our D. All right, so if we use just lightly, if this is our actual surface, right, there it is. Now in red, since I have x, y, so this is what we have. So I have x, y, and then a function of x, y. That means this is going to be our D. So D comes from x and y, and then f is the actual surface because it's the function of x and y. So our domain is in x and y. In the last example that we just did, our domain was in x and z because the y was a function of x and z. So this triangle down here is our D. All right, so S, which is this surface, that's S. Our D is this. Okay, now we'll talk about the limits of integration and all that stuff in a minute. And we're gonna make our go simple in this direction right here. So obviously our x is going to go from 0 to 1, and our y is going to go from 0 to 1 minus x. Right there, we have to go from there. But we have to talk about the normal. Now, to get the real normal that you have to use, you have to do it properly. Now, it's going to end up being one of these, but you can't, just because I calculated a normal does not mean this has length of root 3, right? Let's see. Right, yeah. This has length of root 3. So how do you know which one to do? So because our D is down here, we have to find the normal of this. So we have to find Tx, Ty normal. Okay. So our tangent in the x direction is 1, 0, negative 1. T sub y is, so the partial derivative is respect to y, of course, I'm just saying that, but it's not really what I mean. 0, 1, negative 1. And then we have to cross those. To get the real normal, the way this equation works, just we have to use this. All right, so we have I, J, K, 1, 0, negative 1, 0, 1, negative 1. Now, I know it seems like we did this before, but we really didn't. It just so happened that those were the vectors that I chose. All right, so when we get this, of course, crossing these out, you get, all right, so canceling these out, we get 0 minus negative 1, which is 1. Crossing these out gives us negative 1, but remember, the middle one is negative, so that's 1. And then crossing these out gives us 1 times 1 is 1. So we do, in fact, get 1, 1, 1. But this one, it just so happened that because this was a plane, I found a vector. But after, and that was only to get this. So, but I'm not allowed to use this in the calculation. After I got this and created my actual parametric mapping function here, by parametrization, okay, after I found this, you have to find the derivative with respect to x. With these, to get the tangent in the direction of x, you have to find the tangent in the direction of y by taking the derivative with respect to y, of course, to get these. After you find these, you have to make the calculation to get n. And I just magically happened to get the same one that I got here. Okay, but just trust me, please just do this. Okay, now, a couple things we have to worry about, like I forgot to in the other one. Is this okay? Now, in order to determine that, it says, well, it doesn't say, because I forgot to write it down. When we're looking at this, we want to orient, sorry, I forgot to write this down, that T is oriented in the positive Z direction. So basically up. So the top surface coming up through the top surface is positive, down through that surface somehow would be negative. Okay, because Z here, because Z is a constant of 1, and it doesn't have to be, that is positive, so this is okay. So this is good to go, and we will use the vector 1, 1, 1. We're good to go. And you have to check for this, because it's either going to be this or negative 1, negative 1, negative. All right, let's start some fresh here. All right, next. So far, we have our velocity vector field, right? Did we calculate that? Yeah, we have, that was given to us. 0, 0, 2. And we have that our normal vector that we're going to use is 1, 1, 1. Okay, and then we have to find our v dot, or ds, which is going to end up being, let's just call that, because then we'll need to put the dx dy over there, and I don't want to do that right now. Let's just calculate v dot n. Okay, so let's dot those together. So we have 0, 0, 2 dotted with 1, 1, 1. And that's going to give us 0, 0, 2. Okay, so we're going to take the integral then of 2 and then we're going to need dy dx. Now, as I stated before, this is something we've taken, done an integral on before a couple times, I think. So we need to create this. All right, this is 1, this is 1. So we're going to create our vertically simple in this direction. All right, so x is going to range from 0 to 1, and y goes from, this is 0, to this curve, this line. The equation of that line is y is equal to mx plus b. So since we're up at 1 and we go down to 1, this is actually right if you consider rise over run. So rise, we're dropping, and we're running 1. So that slope is actually -1. So this would be -1x. And since our y-intercept is 1, we have -x plus 1. And I think I mentioned before, we can just write it as 1 minus x. So this is our upper limit 1 minus x, and we just have to do that one. All right, so let's just go ahead. Let's do the inner. So 2 dy, so this is dy of 0 to 1 minus x. Right, and this might have, I'm not sure if this got cut out, but if x goes from, no, that's right there. I already talked about that. Okay, so that gives us, so that's just going to be y, so it's going to be 2y from 0 to 1 minus x, so that gives us 2, and 1 minus x minus 0, and that gives us 2 minus 2x. All right, and that gives us the integral. And then this is it. Let's just pull that 2 back out. Forget about this one. We're using this one. So pull that 2 out. So we just have 1 minus x dx from 0 to 1. And that equals 2. And this one gives us x minus x squared over 2. And that is from 0 to 1. So plugging in 1, we have 1 minus 1/2 minus, plugging in 0 just gives us 0 minus 0. There we go. So we have 2 times 1 minus 1/2 is 1/2, and 2 times 1/2 is 1. All right, now 1 watt, because our initial velocity was in, so our velocity was centimeters per second. Meters per second. All right, so when we look at this, when we have our integral of a velocity, okay, dotted with ds, now our normal vector is basically whatever that represents. The vector is inside here with ds. This ds is a surface, of course, which eventually turns into where are we here? Our dy dx. So this ends up being our v, It's sort of in our v, but also involves that the normal vector, but it also has a dy and a dx. So again, this is still a three-dimensional kind of thing, but this one is a meters per second, and these are both in meters and meters. So we have this times a meter, which actually gives us meters cubed per second, which is a volume per second. Okay, that's what that ends up being, is a volume per second. How much flow, how much the water is, the volume of it is going per second through that surface. Now, with this problem, I just want to show you one more interesting thing. Is that kind of why this kind of worked a little bit. Let's do the problem over, but instead of using that triangle as our surface, let's actually use that as our surface. Okay? Now, to parametrize this surface, we're going to do the same thing. Parametrize that. So, but this surface though, and we'll worry about the limits, worry about x's and y's. But this surface is still going to be x, y, but then since our z value is always 0, it's just going to be x, y, 0. Okay, so I didn't have to find, like on that last problem, because this upper surface was a plane, I had to find the normal vector anyway. Now, if that's some other surface that we know, we're not always going to be able to we're not going to be able to do that unless it's a plane, of course. Now, even though this is a plane, I'm just going to do it the right way. We should all know a normal that shoots out of here, but I just want to do it the right way. So our tangent vector in the x direction is going to be 1, 0, 0. Our tangent vector in the y direction is 0, 1, 0. Again, just taking a derivative, partial derivative of x or y. And then I'm going to dot those together. And then you should already know what this is, too. This is probably one of the first things that we actually dotted together, or not dotting, we're cross product, sorry. All right, so canceling that out, we have 0 minus 0, which is 0, and this one is going to be negative if it exists. Crossing that out, so 1 times 0, 0 times 0 is 0, so that's also 0. And then crossing the k's out, we have 1. All right, so 0, 0, 1, which is any vector that just basically comes out of here and is going to go 1 unit in the z direction. Now, in order to find our v dot n, our v, if you recall, was 0, 0, 2, and this one we're going to dot was 0, 0, 1. And then so 0, 0, and we get a 2. So now we have the integral, double integral of 2 dy dx. And our dy dx, our limits of integration are going to be exactly the same. Y still goes from 0 to 1 minus x, and x goes from 0 to 1. So we're going to get the same answer as 1 meters cubed per second. Now, why in the world does that occur? Well, this is just unique in this case, that it's not always going to do this. But it's because our velocity vector field is constant. It's a constant of 2 everywhere, right? So this is our vector. Our vector field is always 0, 0, 2. So it's 0, 0, 2. That was actually the normal I drew. 0, 0, 2, 0, 0, 2, 0, 0, 2. So it's flowing up through there. So every vector that comes up through here, and because our vector field is 2 everywhere, and not just here, it's everywhere, that when this vector field comes up through here, through this surface, it's the exact same basically cross-section as what was down below here. Although if we call this S and that red one down there D, they obviously do not have the same area. This S has a larger area. But because of that larger area, if you kind of look at a side view of this triangle, if this is, let's say, if this is, you're basically looking from this direction here. This is a triangle. Now, this is not the X or the Y axis. The X is like here, the Y is like there. So if you look at this, and this triangle that's down here, say like this, so all these arrows coming up through here, everything that passes here will also come through here. So everything here is flowing through this, which is here as well. So it's the exact same answer. I wish I had some sort of three-dimensional model I could hold up like a piece of paper, and I could show you everything that comes through. But that's why we're going to get the same answer on this one. But that's only going to work because of 2 things. One, this red triangle down here is literally the XY footprint or projection of the upper triangle. And the second thing is that the flow, or the velocity field, sorry, is 2 everywhere. Okay, if it changed somehow, depending on your X's and Y's and Z's, that would actually not be true.